Hello everyone. So myself Arshad Gaikwad and my friend Maika Kalte. Today we are going to present aerospace propulsion electrothermal thruster and we are team 4. So in this PPT we will be seeing the following contents. The first is electrothermal thruster, then we'll be seeing resistor in space propulsion, then electrical heating elements and arc jet thrusters. You may be thinking, what is the electrothermal thruster? In the word itself, electrothermal, the electro means the electrical and thermal means the heat. So we will see that its purpose is it is used in a spacecraft propulsion. The operation is means as I told you, the electrical energy is used to heat the propellant. The and you may be getting doubt the thrust generation. So thrust generation is it expels the heated propellant at a high velocity to create the thrust. And in electrothermal thruster we have two variation. The first one is the arc jet thruster and second is the resistor jet thruster. The schematic diagram is of resistor jet thruster. It is a type of electrical propulsion engine used in a spacecraft in a space. The main component of resistor jet thrusters includes first is the pressurized propellant storage. This tank holds the inert gases, typically the helium, used for the propellant for the thrusters. Then next is the heater. This component uses the electrical current to heat the pressurized gas. Then next component is the conversion diversion nozzle. This nozzle shapes the hot gases flow and accelerates it to create the thrust. The resistor thruster works by converting the electrical energy into the thermal energy to heat the propellant. The hot gases is then expelled through the nozzles, creating the thrust that propels the spacecraft. Then the station keeping means maintaining the spacecraft position in the orbit. Then the attitude control is the adjusting the spacecraft orientation. The orbital maneuvering, it is raising and lowering the spacecraft orbit. The small satellite power is providing the propulsion for a small satellites.
So this is basically the image of a thermal radiation shielding device. So we'll be seeing its following components. The first is the propellant. So this is the fuel that is burned by the thruster to create the thrust. Then we have the thruster. Thruster is a device that converts the propellant into thrust. Then we have the exhaust. Exhaust, this is the hot gas that is expelled from the thruster. Then we have the heat exchanger. The heat exchanger is a device that transfers heat from the exhaust to the resistive heater assembly. Then this is the resistive heater assembly. Resistive heater assembly is an electrical device that generates heat. Then we have the thermal radiation shielding. This is a layer of the material that is designed to protect the spacecraft from the heat of the exhaust. Now we'll be seeing the working of this system. The propellant is burnt in the thruster, which creates the hot exhaust. The hot exhaust gases flows through the heat exchanger where it transfers heat to the resistive heater assembly. Then the resistive heater assembly generates heat which is used to keep the thermal radiation shielding hot. The thermal radiation shielding protects the spacecraft from the heat of the exhaust. This type of thermal radiation shielding is important for protecting the spacecraft from the extreme heat of rocket engines. Without this shielding, the spacecraft could be damaged or destroyed by the heat. Now in this slide, we'll be seeing the detailing of the resistor jets. The first is, what are resistor jets? So basically, they are the type of electric propulsion that uses electricity to heat a non-reactive propellant like water or ammonia. This hot gas expands and is expelled through a nozzle, creating thrust and propelling the spacecraft. The next is the working principle. Basically, we have a propellant which is either water, ammonia, or even waste fluids from the spacecraft can be used as a fuel. Then heating. Electricity heats the propellant to high temperatures, which is around 700 degrees Celsius to 1500 degrees Celsius using a resistor. Then the thrust. The hot gas expands and is pushed out through a nozzle, creating thrust. Then the next we'll be seeing why are they cooled. The first thing is high efficiency. Resistor jets get more oomph per unit of fuel compared to other electric options. Then the next is simple design. It is easy to build and maintain, making them cost effective and reliable. Then the next we have is flexibility. Can use various propellants, even readily available ones like water. Then low and long. Perfect for tasks needing low thrust but long burn times like keeping a satellite in its place. Then we have some of its special features. One is the weak links, then we have power hungry, then we have heat seekers.
Moving towards the arc-jet. What is the arc-jet? Arc-jet thrusters are the type of electrical propulsion engines for the spacecraft. They work by creating the electrical arc, which is similar to the lightning bolt, inside a chamber filled with the propellant, typically the hydrogen and the ammonia. This arc heats up the propellant to the extremely high temperature, causing them to uh, expand rapidly and shoot out of the nozzle at a high speed, generating the thrust.
The following are the four types of electrical heating elements for resistor jets, which is a type of electric propulsion engine used for spacecraft. So the first is straight coiled wire. This is a simple wire that is coiled in a helical shape. It is a relatively simple and efficient design, but it can be prone to burn out if not properly cooled. Then the next we have is transverse coiled wire. This is similar to the straight coiled wire, but the coils are arranged in a transverse direction, perpendicular to the flow of propellant. This design provides better heat transfer to the propellant, but it is more complex to manufacture. Then we have a spear bed. This type of heating element consists of a bed of small spears made up of a high temperature material such as tungsten or hafnium. The spears are heated by the electrical current and they transfer heat to the propellant by conduction. This design is very efficient and provides good heat distribution, but it is also the most massive and complex of the four options. Then the next we have is chamber wall. In this design, the entire chamber wall is made up of a resistive material that is heated by the electrical current. This design is very simple and lightweight, but it can be difficult to control the heat distribution and it is not as efficient as the other options. The choice of which type of heating element to use depends on a number of factors such as the desired thrust level, the available power, and the size and weight constraints of the spacecraft.
Detailing for the arc jet. What are they? Means the propellant is like the resistor jet. The arc jet can use a variety of propellant, including the hydrogen, ammonia, and even water. The arc chamber. The propellants flow through an arc chamber where an electrical current creates a high temperature plasma around 2500 degrees Celsius. The nozzle. The nozzle is the hot plasma expands rapidly and exits through a nozzle generating the thrust. The advantages of the object. First of all, it has the high specific impulse. They achieve by the high thrust per unit of propellant compared to the chemical rocket, making them more fuel efficient for a long duration mission. It has a fuel versatility. They can operate an diverse propellant, offering the mission flexibility and potentially utilizing in situ resources like water ice. It has the simple design. The arcjet have fewer moving parts compared to other electrical propulsion system, leading to improve the reliability and reduce the maintenance need. The challenges faced by the arcjets are first of all it needs high power consumption. Operating an arcjet requires a significant electrical power necessary efficient power generation system on board spacecraft. Second is the thermal management. The intense heat generated within the thruster need carefully management to ensure the efficient operation and prevent damage. Uh, Third challenge faced by the arc jet is the erosion. The hot plasma can erode the component within the thruster over a time, requiring the careful material selection and the design consideration. The applications, the deep space mission, there the high efficiency make them ideal for a long duration voyages and distinct celestial body. Second application is station keeping and attitude control. Third application is orbit transfer and maneuvering. Fourth is the small satellite propulsion. It is the diagram of DC arc-jet thruster. It is the type of electrical propulsion engine that uses the electrical arc to heat the propellant, typically the helium, to very high temperature. The hot propellant is ejected through a nozzle to produce the thrust. DC arc-jet thrusters are relatively simple and efficient, and they can be used for a variety of applications, including the spacecraft propulsion, attitude control, and the station keeping. However, they can be limited the space impulse, means that is the measure of the efficiency of a propellant compared to other types of electrical propulsion such as ion thruster and Hall effect thruster. The main component of DC arc-jet thrusters are a cathode is typically made of trihydrate tungsten. The cathode emits the electrons when it is heated by an electrical arc, and an anode, which is the typically made of a tungsten. The anode collects the electron and emitted by the cathode. The constrictor, that is, which is the narrow passage that helps to confirm the electrical arc and increase the temperature. The propellant injector, it is means which injects the propellant into the arc jet chamber. The nozzle which accelerates the hot propellant out of the engine. To operate the DC arc jet thruster is to first turn on by applying a voltage to an electrode. This creates an electrical arc between the cathode and anode. The arc heats the propellant to a high temperature, typically of order of 10,000 Kelvin. The hot propellant is ejected through the nozzle, producing the thrust. DC arc jets are relatively mature technology, and they have been sent a number of spacecraft. For example, the Messenger spacecraft, uh, which is orbited Mercury from 2011 to 2015, used a DC arc jet for a station keeping.
So in conclusion of this entire presentation, this is a summary of the electrothermal thrusters. So they stand as efficient space propulsion systems, leveraging electrical energy to heat propellants for thrust generation. Despite challenges like power requirements and material limitations, they offer precise control over thrust levels and flexibility in propellant choices. The applications in satellite operations and station keeping, alongside the adaptability to various missions, highlight the significance in modern space exploration. Thank you.